In this session, we are going to look at the actual vulnerabilities and attacks that are impacting JSON Web Tokens. And I've tried to be relatively comprehensive, but there really are just so many. There are so many ways in which the implementation and the usage of JWTs or JWTs can go wrong in an application. So this isn't going to cover every possible issue that you might encounter in an application, but it should give you a very strong foundation for testing them. And if you want even more information, I'm happy to announce that there is going to be a curriculum project that has structured resources for how to approach learning different application security topics. That is going to be published to the Digital Boundary Group GitHub within probably a few days of publication of this video. So if you check this link, if you want some additional resources here, if you want to learn about some additional issues impacting JSON Web Tokens, you can check out this resource, but if you check it and it's not available, just check in a few days. Okay, so important notes. There are many well-documented attacks against JWTs that lack corresponding CVEs. So there aren't actually, or even reported cases in bug bounty programs. So there are a lot of even tutorials on how to do this specific attack where I couldn't even find evidence of this occurring in practice. And I think a big part of that, there are kind of two reasons for that. One is that CVE reporting is very much biased towards public and open source software, largely like JWT libraries. And so a lot of application vulnerabilities where JWTs have been, I'll say played a role in those vulnerabilities. Probably a lot of the tutorials and the different attacks that have been written up without specific examples come from practitioner experience. And of course, our industry is very secretive. So a lot of attacks that occur against clients of pen testing firms don't really get reported or shared too often. So there are a lot of unknowns here. And in particular, the prevalence of specific vulnerabilities is unknown. I will speak a little bit to this with some of my own experience from testing a large number of applications that are using JSON Web Tokens, but that's not necessarily representative across applications as a whole. Another thing worth mentioning is that the tooling for working with JSON Web Tokens, and in particular in constructing different attack primitives from them, is very fragmented and I would say incomplete. There are a lot of things that can be automated that aren't. There are a lot of tools that do many test cases but don't do other ones. If you want to really be effective in testing JSON Web Tokens, unfortunately, you have to use a wide array of tooling, and unfortunately, you also have to do a large number of things manually. I'm not going to cover a lot of those in this session, I probably will do so in the future if I ever find the time. But I will cover a few things, and so I will note also that I tried to do a comprehensive review of the available tools. Most of them are burp extensions, as you can see here. And what I did was I took a large number of attack primitives and tried to map out which tool covered which case. And it turns out this is actually a very hard task just to do because there is a different language used across tooling. A lot of them are not very clear in advertising what their capabilities are, what they're testing for. It honestly is a real mess. And I can't recommend any specific tool as the de facto JSON Web Token testing tool. A few of them I will mention throughout this session. Unfortunately, I wish I could say, hey, here's what you should use. Here's how you can use it. Hopefully, I'll do that in as I mentioned, a future video. Probably most people are using burp if they're testing JSON Web Tokens. And burp does have some built-in capabilities for interacting with these tokens. So here's an example from a test application where I'm using burp's inspector. I hate the inspector. I think this is an awful tool. Just the workflow of it kind of sucks. You have to select the text. You have to go and edit it. You have to click apply changes. I don't use this, but you can use it. For me, what I like to do, if I'm just making quick edits to like a body or a header of a JSON Web Token, I constructed this very simple custom action, which what it does is it base64 decodes, base64 URL decodes your selected text in repeater, and then it surrounds it with base64 URL tags for hackverter so that when you send that request, it'll automatically get encoded again. This is very versatile because you can use this not just in repeater, but also in intruder, scanner, and other tools. So this specific, I guess, Bambda technically, because it's Java code that runs the custom action, I've published it to my YouTube repo. You can see the link in the bottom, and I'll put that in the description of this video as well. A very popular tool that you can do a lot of things with, but I find to be quite clunky in its user interface in Burp is JWT editor. So here's what the custom editor looks like in a Burp request. And yeah, it's a bit of a mess. If you have a very big token, very large token with a lot of content in it, I find that it's hard to scroll through all of the little individual scrollers for like the header and the payload. But the one advantage that it does bring is signing capabilities directly into Burp, which can be quite convenient. So any situation where you're able to sign, or you're testing signed payloads with some type of certificate or secret that you control, then the JWT editor does work for a lot of this. So I do use this from time to time for certain test cases. Okay, so when we're talking about the actual attacks against JWTs and the applications that implement them, there is a wide range of issues, and generally what I've done is, or what I've tried to do is separate these into two categories. So one is attacks against JSON Web Tokens themselves, which is attacks against the assurances that they bring. So this would be the attacks that undermine the signature of that JSON Web Token, for example. And then I've also tried to categorize attacks into the class of attacks that are not undermining the security assurances that you want from JWTs, but are mishandling them in some ways that lead to other vulnerabilities in the application. And you could probably broadly separate these into the types of vulnerabilities that impact JWT libraries and their usage versus the types of vulnerabilities that attack the ways in which applications consume the data coming from JWTs. That's not going to perfectly work in a lot of cases. And of course, if you're testing an application from a black box perspective, you don't have the actual insight into how an application is using JSON Web Tokens, how it's validating them, even what libraries they're using is often opaque. But I think, nevertheless, it's a useful convention to think about the differences between, or really where the root cause is of the different issues. And so that's how I've tried to separate them. So to start, we're going to look specifically at attacks against JSON Web Tokens, which would be the core logic of JWTs and their supporting libraries. And the first one is very simple. It's probably not worth spending too much time on, but I will show you the general form of these slides to come. At the top, I have a summary of the weakness, an example exploitation scenario. I've tried to source CVEs that you can look up where relevant. And then at the bottom, I've broken down decoded versions of the token. So most of my slides will have kind of an original valid token and then a manipulated one. And so I've tried to showcase also an attack that you might try to do, because oftentimes when you identify a JSON token or JSON Web Token vulnerability, it's not enough just to abuse that vulnerability. You also have to think about the context in the application. And so what I've done here with this example is I've come up with a scenario where a JWT or a JWT is used as an authorization token, and that is self-encoding of the properties of the user. So it includes the user ID, and a very obvious attack would be if we can submit a token and manipulate it and have the application trust it, then we could manipulate it to reference a different user ID in order to gain access to that user's data. There are many things that you might want to do. It really depends on what's encoded in the token and how the application is using it as a security mechanism. So I've just taken very simple examples for these slides, but you'll see all kinds of wacky things out there in practice. Now, in this case, it's very simple, right? The application just fails to validate a signature. You might think that this is an uncommon vulnerability, and I can tell you from experience that this is not. There are so many situations where the application is using JSON Web Tokens, it's relying on them for a security purpose, and it just doesn't validate the signature. So you can just, as in this example, put anything under that signature, and the application accepts it. This is, I want to say, it's got to be like 30% of applications that use JSON Web Tokens that I've assessed are vulnerable to this, which is wild, of course. In my experience, again, it's very common. So all you need to do is just manipulate whatever you want to do in the token, in its content, in its body, its claims, and the application accepts it. A variation of this, well, I guess not really a variation, but kind of a similar, very silly fail case is where you modify the algorithm in the header to just be anything, and the application fails to see an algorithm that it uses, and so it's just like, okay, well, I guess I'm accepting this token, and therefore you can have anything as a signature again. The difference between the previous case is that you actually have to put some junk in the algorithm, in the alg header in that JSON Web Token in order for it to be accepted. And of course, there is a CVE that is quite recent that references this issue. One that if you've been testing JSON Web Tokens, if you've been reading about the vulnerabilities that impact them that you've probably heard of, is this alg none scenario where you specify that the algorithm in use is actually none, and then you don't need a signature, and you can submit a modified token. I have seen, you'll see many tutorials and many tools reference variations in the casing of the string none. I have never seen that be a barrier to exploitation. I've never seen any of the casing variations, which I assume arise from like a block list of strings matching none, and it is case sensitive. But nevertheless, tools like JWT tool will automatically build you payloads that include different casing variations of the string none in that header. The next one is a little bit more complex. So now we've passed through the very simple ones. Actually, we have a few more simple ones to come, but this one is a little bit more complex. And interestingly, there are a number of CVEs that have been attributed to this vulnerability. So this is a situation where the library or the developers have intended to use RSA or some other public key algorithm, asymmetric algorithm, in order to sign tokens and then later validate those signatures. And what happens is if an attacker modifies the header to specify a symmetric algorithm, so an HMAC algorithm, then the application falls back to use that, but what it uses as the secret is the public key. So the public key of that, the RSA public key that sometimes is available. You can find it at a number of different common publication endpoints, and I'll talk about those briefly in the next slide. And in some cases, you can actually just reconstruct it. And it seems like a weird thing to do, to take the public key and use that as a secret to an HMAC. But again, this has been reported across a large number of CVEs. Presumably, there are a large number of applications that are still vulnerable to it. So I would say that this is very much worthwhile testing. As far as the actual steps for this, so this will be one where I describe some of the operations involved in order to actually exploit this. So the first step is obtaining the public key. So you can either fetch it from an endpoint. On my YouTube GitHub page, I actually published a word list with a large number of endpoints that you can use as a word list to guess for these. But there are many endpoints where an application may publish a JSON web key set or other certificates that you might be able to use for this. And you'll need to convert this into, well, actually, you can probably should use it, that certificate as is. Well, actually, it's going to depend what form it's in, right? So if the certificate is published, or if the key is published in a certificate, you could probably use that as is. Otherwise, if it's published within a JSON web key, you'll have to reconstruct the PEM form, which I would have to guess probably in that situation, this type of algorithm confusion vulnerability is less likely to occur. So some of those steps I obviously have noted will vary, so I haven't put all the details. You can find lots of guides for this. But the other thing worth mentioning is that there is an approach you can use to reconstruct a public key if you can obtain multiple tokens that are signed by the same key. One of the challenges with this is that there are different ways to actually serialize that key. And remember, if you're using some type of secret in an HMAC operation, you need that to be an exact byte replica in order for it to be able to work. So I think that this tool here, so this is the one I reference here is Portswigger's Docker container. but they have taken that from another tool that I'm sure if you go to their repo, you can or if you just search, is it Sig2n? That feels like a typo. I thought it was, maybe that's correct. You can find it pretty easily anyways. And I think the original tool, and probably this Portswigger adaptation of it that's available with a Docker container, which is probably the easiest way to run it, I think it creates a few different representations because, as I mentioned, there are different ways to serialize it, and that's going to result in different bytes that will lead to different outcomes when you're using an HMAC algorithm. Finally, to actually sign your JWT, you can use a JWT tool. You can use the JWT editor in Burp. You have a few approaches there. The next vulnerability is a very simple one. It tends to be less interesting because typically you have to actually obtain someone else's JSON Web Token for it to be of any use, but it's just you have some type of time-based claim, IAT, NBF, EXP, so the expiration, for example, and the application does not reject expired tokens that are validly signed. So something that you're probably, or typically not in a situation to exploit, but it does change the nature of the risk if there are any scenarios where those tokens can leak because they remain valid forever, of course. And naturally, there are CVEs reported against that issue. When you're dealing with HMAC-based algorithms that are relying on a secret, this, of course, is a common issue. It's using guessable secrets, and that can be a developer putting something in that is not a sufficiently secure secret. They're not using like a random number generator. It could be that there is a default secret that comes with a library or a framework that is being relied on. There are many ways in which this can you can have something that is functionally guessable. Obviously, your how successful you are is going to depend on the word list that you deploy to guess these secrets. There is an existing repo. I don't know if it's been updated recently. I think it might be relatively old, but this one published by WallArm, JWT.secrets.list is one that's popularly referenced as a secret list, which I think they've sourced different libraries and other instances where specific secrets have been used for the calculation of the HMAC for JWTs. So that's probably a very effective list, but it doesn't necessarily account for all of the different secrets that developers might come up with. So you might want something a little bit more robust for practical guessing. And you can use JWT tool for actual guessing, but there are other tools as well that are probably more efficient if you're doing a large number of guesses. I would have to guess that JWT tool is not the most effective cracking tool. And then, of course, once you discover a secret, you can then forge your own tokens by using that secret. A variation of this issue is where an HMAC is used, but the secret is just empty. And this might just be included by default in your lists that you're using for guessing. It may also be worth considering if, even if the tokens that you're attacking are using RSA by default, it might be worth considering whether there is a fallback to use a secret when an HMAC algorithm is specified, and if that fallback is blank if developers don't define it. So something to keep in mind. Sensitive information embedded in JSON Web Tokens. This is another one similar to expirations that, or like, missing time-based checks that doesn't necessarily let you immediately exploit something, but certainly changes the nature of the risk around how those JSON Web Tokens are handled by the application. And I've actually seen this pattern a few times, and I think this is what is reported in the CVE cited, where the JSON Web Tokens include a number of user properties, and that includes either the user's password or a representation of it, like a hashed password. And obviously, if you can get access to other users' JSON Web Tokens, then that greatly changes the impact of that, because now you can actually obtain their passwords. JSON Web Tokens I don't know how often this is the case, but it's always mentioned that they shouldn't be misunderstood as something that are encrypted because they are just base64 encoded by default, and anyone can read them. But I suppose it's possible that developers that are implementing them look at them and assume that there's some encrypted form of something. This vulnerability is a relatively unique one. It impacts unpatched versions of Java 15 to 18. CVE was reported in 2022, so I would guess that there are probably a number of vulnerable instances that are out there. This is known as the psychic signature, and it results from a cryptographic issue where the parameters of elliptic curve algorithms, the parameters R and S, are set to 0. And therefore, this lets you just use this string here, this MAYCAQACAQA, as the signature. And it's as easy as that. So that's a very easy test case to try when you see that an elliptic curve algorithm is in use. Another one is improper error handling. So this is kind of a unique case that was reported for the CVE here that's worth mentioning. And this was a situation where if you had an expired token that had a valid signature, the application would reject it. If you had a non-expired token that had an invalid signature, the application would reject it. But as soon as you presented a token that both had expired and had an invalid signature, the application would not properly handle this. It would assume that that was a valid, or it wouldn't validate the signature. And in some cases, that could lead to trusting certain claims within it. The CVE, I think, impacted the library, so it's not clear if any applications actually were impacted by this, but it's always worth checking the different impact of various error conditions, especially when different issues with the tokens are co-occurring and how the application deals with that. So you might recall that the JKU or the X5U headers, these specify URLs to retrieve keys or certificates from. This is another interesting one where I couldn't find an immediate CVE, but it seems like one that it's discussed a lot, and there are a lot of tutorials and labs for this. So maybe I just didn't do a really thorough CVE search for this one. But I assume applications have been impacted by this in the past. There are, the main issue here is that you have a header that tells the application where to retrieve the certificates from. And so as an attacker, if you can host your own keys or certificates and reference those and the application trusts those, well, then you can use those to sign your own tokens. So it's pretty straightforward. And that might look something like this. The first step would be, I think, to identify potential external interaction. So using something like Burp's Collaborator or your own server to see if URLs are actually being reached for downloading key material. And then what you want to do is create your own certificates, host them wherever. You can use a GitHub gist for this, for example. And then you can use a tool like JWT tool in order to sign the tokens with your own certificates. Just as an aside, for a little bit of clarity on the distinction between the JKU, JWK versus the X5U and X5C headers. So the J variants are the ones on the left hand side. These are the JSON Web Key and JSON Web Key object and JSON Web Key set forms. And on the right, we have the X509 certificate form. So those are the differences there that obviously you need to be aware of if you're trying to exploit these issues. And so a similar related issue when talking about the JWK and the X5U headers, these are headers where you actually embed the key material directly into the token itself. And so it's a little bit simpler in that you don't have to be hosting your certificate somewhere. You embed those in these headers, send them to the application, and hope that it uses that key material in order to validate the signature. And then, of course, similarly, you can sign your own tokens. And this one actually does have a large number of CVEs reported against it. Okay. ECDSA nonce reuse. This one is kind of questionably included in the slide deck here. There are no cases against this reported for JWTs. In theory, it's possible. It's a very specific cryptographic issue that I'm not going to go into the technical details of, but I thought it was interesting, and it's one that in theory could occur. And the one big reported case against this is actually the hacking of the Sony PlayStation 3. So if you're interested in this vulnerability, I'm sure there are a variety of write-ups for that might be worth checking out. All right, and those are the attacks against the JSON Web Tokens themselves, attempts to undermine the validation of the signature. And now we're going to look at attacks against applications, essentially through JWTs. And I think as we go through some of these, it might make sense why there's the distinction here. And this first one here is maybe questionably included here. It could be probably in either category or perhaps in its own category. And it's distinct from endpoints that are actually consuming JSON Web Tokens. And this is the JSON Web Key or any other key material or certificate hosting endpoint, like a JSON Web Key set. These can potentially disclose sensitive information like private key material. I have seen this in one instance at least, and so what I've done here is I couldn't find a suitable word list, so I built one that's referenced or that's available in my GitHub that you can access here. I couldn't find any CVEs, interestingly enough, related to this, but if you're testing an application that is using cryptography really in some way where you expect there might be key material available, so if it's using JSON Web Tokens, if there are OAuth flows, I'm sure there are all kinds of scenarios in which this might apply. It's probably worth at least taking a quick look at these endpoints. And if you're testing against an application that uses JWTs, it's also an easy way, of course, to get the public key material so that you can perform certain attacks like algorithm confusion. In the example at the bottom, I've just shown a situation where one of the fields crucial for constructing private keys is disclosed. And so obviously you don't want to be doing this. Next vulnerability, verbose application error. There are CVEs, funny enough, reported against this. And this is actually an interesting example if I remember it correctly. So the issue here is you tamper with the token in some way, the application doesn't handle it correctly and returns useful information to you. And I think in this CVE cited here, the application actually returned, if you sent it a token with an invalid signature, it would send you the token back and say, oh, actually, here's what the signature should look like. So it was actually leaking signatures that you could use. So you could use the application itself as a way to actually sign tokens, which is kind of interesting. What you get is going to be application dependent. How you test for this, I'm going to talk about in a bit here. I have a few slides on methodology in Burp itself. Next issue, this one was already kind of mentioned, using the JKU or X5U headers in order to actually inject your own key material by having application call out to them. Well, you can potentially use these headers as well in order to conduct classic like server-side request forgery style attacks. So let's say you also have a verbose error mechanism where the application gives you lots of details of the errors that are occurring, and it also accepts these headers and lets you supply your own URLs. Well, maybe you can probe internal services and it will return the responses from the services being like, look, the certificate didn't work. Here's what it sent back. So that could be worthwhile as well. Of course, traditional injection and other vulnerabilities. Interestingly, I haven't seen CVEs reported for these. I thought there must be some. I feel like I dug a decent amount and I didn't find any. But any situation where you have an application that is handling inputs, you have the potential for injection or other vulnerabilities. The one that's commonly referenced in tutorial material is the KID header, where in theory you could have identifiers and key material that are stored in some type of database, like a SQL database. So in theory, you could have SQL injection through it. Again, lots of write-ups. There are even labs for this. I couldn't find specific bug bounties or CVEs. I'm sure there's some that exist, and so if anyone can find any, please send them my way. I would love to see them. And this doesn't, you'll see most write-ups are just talking about the KID header, which is quite interesting because really it just depends on how the developers are implementing and using JWTs in their application, but they can take anything from this. And it can be claims as well. And I think I mentioned it on a subsequent slide, but it's also worth not assuming that claims are not going to be processed prior to, don't assume that claims will only be processed if you submit a JWT with a valid signature. I, from my own experience, have found that that's not always the case. I've seen an application that is doing signature validation properly, but if you modify certain claims, it throws an error before the signature validation error. I think I have a slide on that, but I mentioned it just in case I don't. Path traversal is also one. It falls, I would say, in the injection category, but I thought it was worth specifically calling out for two reasons. One, you'll see a ton of tutorials and labs for this specific issue. The idea here is if your KID is being used to look up key material on a file system, then maybe you can just reference something like dev null, and then you don't need a certificate in order to be able to actually sign tokens. Another situation where I didn't find specific CVEs for this, it's a test case that's built into a lot of tools. Again, there are a lot of labs and tutorials for this. I guess it's worth trying. I've never personally found this to be an issue, but in theory, it could be occurring. And yeah, like there's, here's one right now, right? The KID, Portswigger has a few JWT labs, and of course, it includes this specific one where the path traversal vulnerability arises in the KID parameter in the header. As far as fuzzing and scanning JWTs, if you're using Burp like I most often do day to day, I already mentioned using Hackverter, which makes it very easy to send decoded requests. And you can also use Hackverter in Intruder as well as in the scanner as well. And I find this to be quite a useful approach to fuzzing it. So not only can you launch burp scans where you target very specific locations within a JSON Web Token, but you can also use your own fuzz lists with your specified injection points in Intruder with Hackverter to fuzz JSON Web Tokens, which to fuzz JSON Web Tokens, which can be very useful for identifying a number of ways in which the application mishandles it. Unintended header processing is one that I have not really seen reported on, but is definitely worth trying. And there is a related CVE to this. And I don't think I've seen, I'm sure there must be a tool that does it. I don't think I've seen a tool do it, but it's definitely worth, if you have a token, guessing header names, like header values, as well as claims that might be processed by the application, even if they don't appear by default in that JSON Web Token. And so in this specific CVE that is cited here that I thought was quite fascinating, when a token contains a crit array listing extensions that FastJWT does not understand, instead of rejecting the token, the library accepts it. So this is a situation where it would be helpful to discover that an application is actually consuming a header, even if it's not included in JSON Web Tokens that are produced and signed by the application, because that can let you actually bypass the requirement for that signature validation. I'd have to guess that this specific case is quite rare, but probably there are other related cases that do occur. The next vulnerability I already mentioned, claims processing prior to verification. I've seen all kinds of weird things. In theory, yes, you expect header values to be processed prior to the validation of the signature, which I would argue is kind of a risky design inherent to JWTs, but nevertheless, that's an expectation because the application needs to check the algorithm, potentially the type of the token that's coming in order to be able to validate the signature of that token. But I don't think there's a good argument for checking the value of any claims in the body prior to validation of that signature on that token. Nevertheless, I've seen a large number of applications that will throw very interesting errors if you try to fuzz the values of those claims prior to the validation of that signature, and that can lead to different information disclosures. It can lead to different vulnerabilities. So as I mentioned, I put together some word lists for headers and claims that you can check out in my YouTube repo on GitHub. Another one that is worth considering and has been referenced, but really is kind of a topic on its own, so I didn't go into detail here, and I've linked Bishop Bok's article on JSON interoperability vulnerabilities that I think is probably essential reading if you want to be able to test for and exploit these issues. That would be parser inconsistencies of the actual JSON parsing within the tokens themselves. And so you can see in this example here, I've modified the body of the token to include an additional ID referencing an additional user. So maybe, there's some type of, even if you can forge tokens, there's some type of additional check on that user ID, but you can smuggle one in by adding an additional claim that is a duplicate of the original. Maybe that can occur. Duplicate claims are often cited in these types of issues. I don't think there were no CVEs that I identified relating to this with JWTs specifically. In theory, issues could arise, so potentially worth testing for. But unfortunately, I can't really give you a priority on this one. How much effort should you be putting into this? That's one of the challenges that is inherent to the nature of our field. There's a lot of the knowledge is not really shared. So how common this is, how worthwhile it is to actually spend time testing for, I can't tell you. Now, these issues, though, do occur, and I only found one CVE that was a unique case, but I've seen this reported on in other situations, and I feel like I've seen it personally. This is a type of attack where you forge an issuer. There are many ways that you might be able to do this. So if you have an identity manager, if you have like an identity management service that your end application trusts, and that service exposes like a registration mechanism to register your own kind of authentication mechanism, maybe that same application will trust your own issuer that you've created with your own certificates. That's something that possibly could occur. And so in this case right here, actually, I think I've made a mistake in the, well, I guess this is good. This is correct, actually. So if you look at the examples, so we have one token that is the expected token that comes from the issuer that is supposed to be, that should be specifically allowed listed by our target application. And the other token that is accepted that, or maybe it's able to reuse the key material of the main of the service that the original issuer uses. There are many ways in which this can work in practice, but in this case, you have an issuer that is basically one that you've forged, right? And so you're using a different service that you've set up or registered in order to sign those tokens and gain access to the application, which it trusts it. A related issue I've seen referred to as audience confusion or token substitution. And so this is a situation where the application fails to validate the audience claim. So a token is created by some issuer for a specific end application. This is something that also occurs in more complex situations where you have, of course, an issuer that is separate from your, you have an identity management system and an authentication framework that are potentially quite distinct from your actual application that is consuming the JSON Web Tokens. And so in this case, the expected token specifies an audience that is our target application. But maybe what we can do is we're able to get a token for a different application, but it's from the same issuer, and we can just replay that against the target application, and the target application accepts it. We just substitute the token. And this type of issue can also occur in application. So if you have different workflows in an application where the expectation is that different tokens are used. So I created this example here. Well, I created all these examples, but in this specific case, I created the workflow claim, which I've never actually seen, but I've used to illustrate this example, where you have maybe different workflows and those claims are embedded in the token. But then the reality is the application doesn't actually validate that claim. So you can take JWTs from different workflows and replay them in different situations. And of course, this falls under the application-specific type attacks, because what you're able to do with this and whether you can do this are very dependent on the application more so than your ability to undermine the signature of JSON Web Tokens. Okay, and those are all the attacks I've decided to cover in this presentation, in this lesson. But now we're just going to talk briefly about the JWT best current practices as per RFC 8725, and we're also going to talk about the ASVS requirements in version 5 of the ASVS. Now, some of these you'll note that we didn't necessarily cover attacks for, and that's worth keeping in mind, that some of the things that are in this best practices document are there certainly for a reason, and might also be worth keeping in mind when you're thinking about undermining the security of JWT implementations. So I'm just going to go through them quickly. You can reference the document if you're really interested in seeing them in detail. Perform algorithm verification by strict allow list, of course. Use the appropriate algorithms. Do not permit none, obviously. Validate all cryptographic operations and reject on failures. You don't want to have any fail open scenarios. Validate all cryptographic inputs, so where you're getting key material, for example. Ensure keys have sufficient entropy, and this goes for secrets as well that are used with HMAX. Avoid compression of encryption inputs. That could lead to, I actually haven't seen that in practice, but of course that could lead to side channel leaks in certain scenarios. And use UTF-8 for encoding and decoding. Validate the issuer and subject in implementations where that applies. For issuers with multiple relying parties, use the audience claim and of course validate it. Validate received claims using an allow list. Use explicit typing. Use mutually exclusive validation rules for different kinds of JWTs. Limit hash iteration count to prevent a denial of service type attacks. Ensure JWTs are correctly formatted using compact serialization. Limit JWE decompression size to prevent DOS. I added this one as well. We didn't really talk about JWEs, and in fact, there is a broader scope of considerations and issues for JWEs, but just personally, I don't see them that commonly. So I'm not sure if I'm going to make a separate lesson and notes for JWE attacks. But nevertheless, they are used in some applications. Now we have the OWASP ASVS version 5. 9.1.1, verify that JWTs are validated using signature or MAC before accepting contents. 9.1.2, only user allow listed algorithms should be used, and obviously, again, not none. 9.1.3, verify that key material is trusted. 9.2.1, verify that validity time span is present and enforced. 9.2.2, verify that services validate token type and purpose. 9.2.3, verify that service accepts only tokens intended for it. In 9.2.4, verify that issuers reusing private keys must distinguish the audience. Okay, and that's it for this session. I'm probably going to do some more actual hands-on practical JWT security testing because there just is so much. It is so dense. There are so many different tools and approaches. I think it's worthwhile showing my own, but that's it for now.